In traditional discrete manufacturing, human operators drove the entire process. They moved the raw material, positioned the workpiece, and decided when to actuate the machine. To automate this, we have to look at the human body as a control system. The operator's eyes act as sensors, gathering physical data, and their hands and feet act as the actuators, executing decisions. Replacing that sensory actuation loop is the core challenge of industrial automation. Before 1968, replicating human logic required physical hardware. Engineers used cabinets filled with hardwired electrical relays, timers, and counters to control machines. Every physical action required a physical connection. If a factory needed to change a machine's behavior, an electrician had to completely rewire the control logic. As manufacturing scaled, physical wiring reached a limit. Rebuilding complex relay cabinets for minor process updates was too slow and expensive. The industry needed a way to abstract machine control away from copper wiring and into a digital programmable environment. In 1968, the Hydromatic division of General Motors formally requested a solution. They issued a specification for a solid-state controller that was easily programmable, reprogrammable, and durable enough to survive a harsh factory floor. The winning proposal came from Richard Morley, who invented the Programmable Logic Controller, or PLC. Instead of routing electrical current through a maze of mechanical relays, Morley's device used a microprocessor to execute stored digital instructions. Today, a standard PLC looks like this Allen Bradley unit. It is a ruggedized, modular computer system designed to withstand high temperatures and vibration. Those input and output modules on the right allow the digital microprocessor to physically interface with standard industrial electrical signals. If we apply this to that manual punch press, the human operator is entirely replaced. A central PLC node now dictates the sequence, receiving data from limit switch sensors and sending commands to robotic arms and control valves. By pulling the control logic out of physical relays and placing it into reprogrammable software, PLCs decoupled the machine's mechanical limits from its logic. Software dictates the process, allowing factories to iterate and scale without touching a single wire. A PLC itself is entirely blind to the physical world. It sits inside a cabinet processing binary code, relying completely on external sensors to translate real-world variables into electrical data. At the simplest level, we have discrete switches. Mechanical limit switches require physical contact with an object to close an electrical circuit. Electronic non-contact switches, like inductive or capacitive sensors, do the same job by detecting changes in magnetic fields or light. Those discrete switches only provide binary, on or off data, but many industrial processes require continuous monitoring of variables that constantly fluctuate. This table outlines common analog transducers. These devices convert continuous physical variables into proportional electrical signals. An RTD measures temperature, a strain gauge measures force or pressure, and a thermocouple outputs a tiny voltage directly correlated to a heat source. Once the PLC interprets that sensor data, it has to physically react. It sends electrical commands to actuators, the hardware devices that convert those electrical signals back into mechanical force. The actuator type dictates the output precision. Pneumatic air cylinders offer simple binary motion, extending or retracting until hitting a hard stop, which is why they're often called bang-bang systems. For high-load, highly precise positioning, factories rely on the continuous pressure of hydraulic systems. Together, sensors and actuators form a complete bidirectional bridge. They translate the physical environment into data the PLC can understand, and then translate the PLC's digital logic back into real-world mechanical work. With the hardware bridge in place, the PLC needs a set of instructions to follow. The exact logic it uses depends entirely on the type of process being managed. Discrete process control deals with binary states. A tank is full or empty, a part is present or missing. Continuous process control deals with fluid variables, maintaining an exact oven temperature as cold parts continuously flow through it. This diagram illustrates an open-loop control system. Notice how the CNC controller sends command pulses directly to the stepper motor to move the table. There is no sensor verifying the table actually moved. The controller simply assumes the motor did its job. This second diagram displays a closed-loop system. The crucial difference is the feedback path. The controller commands the servo motor, but an encoder constantly monitors the motor's actual position and feeds that data right back to the controller. Because the controller can constantly evaluate the actuator's performance against the target parameters, it can adjust its commands on the fly. This closed-loop self-correction is essential for high-precision manufacturing, as it prevents compounding mechanical errors. A modern factory might have hundreds of sensors and actuators firing simultaneously. So how does a single PLC processor keep everything synchronized without crashing? It uses what is called a scan cycle. Instead of reacting erratically to inputs as they happen, the PLC operates on a rigid, continuous loop of execution. First, during the input scan, the PLC reads the current status of all physical sensors and freezes those values into memory. Then, in the program scan, it runs its stored logic against that specific static memory snapshot. Finally, the output scan updates all the actuator commands based on those calculations. What makes this effective is the speed. A PLC completes this entire three-step cycle in just 1 to 3 milliseconds. Because it loops thousands of times a second, the PLC can immediately catch an event-driven change, like a limit switch tripping, while simultaneously tracking time-driven changes, like a precisely measured cooling cycle. To a human observer, the machine appears to react instantly. But that illusion of simultaneous control is actually the result of this rigid millisecond-scale cyclical scanning. It guarantees deterministic, perfectly repeatable machine behavior. Industrial control is structured hierarchically, scaling from individual sensors to integrated factory systems. At the base tier, we have basic device control. This is the management of individual, isolated components, like a single PID controller maintaining the temperature of a specific heating element. Above that is the middle tier, procedural machine control. This is where a controller manages the sequential, step-by-step work cycle of a single complete machine, like a polymer press opening, closing, and curing. And at the top tier is coordinated system control. Here, multiple disparate machines, robots, and conveyors are orchestrated into a unified, synchronized work cell. Historically, human operators had to physically coordinate these macro-level assembly lines, monitoring when one workstation finished so the next could begin. Modern systems require integrated digital logic to manage that handoff. PLCs were explicitly optimized to handle those middle and top tiers. They serve as the brains that link isolated device controllers into smart, interconnected factory networks. To actually program a process across these tiers, automation engineers use the USA principle: understand, simplify, and automate. In the understand phase, an engineer evaluates a manual task, like running an industrial washing machine, and breaks it down into a flawless, sequential list of discrete physical events. That sequence is then translated into a work cycle program, often visualized as a timing diagram. By charting the sequence over time, the engineer maps every physical step to the required binary state of the PLC's inputs and outputs. It clearly defines exactly when a specific sensor should trigger a 1 and when an actuator should drop to a 0. Only after that logic is verified does the final automate phase begin. The sequence is downloaded directly into the PLC hardware, empowering the software to command the actual sensors and actuators on the floor. By abstracting control into software, PLCs decoupled machine logic from physical wiring. This shift allowed factories to reconfigure assembly lines in hours rather than weeks, providing the flexibility required for the high-volume, multivariant production seen on modern factory floors.